Isn't Hoyer? I lolled. No, I didn't. Continue. Imagine in a very simple world, you wanted to make a bike, and the bike, ingredients? No. Parts? All that you needed were wheels and a frame. Determine. How many wheels would you need for that bike? Bike, not dodeca bike. And then, how many frames would you need? And how many bikes would you get for that? Okay, that's a balanced reaction. The kind of questions that you'd be asked about this are things like, hey, I've got 40 wheels, how many bikes can I make? Or, I've got 30 frames, how many bikes can I make? Or, I want to make 20 bikes, how many wheels am I going to need? Okay? Those are the kind of questions you're going to ask and answer today, except instead of wheels and bikes and frames, it's going to be chemical reactants and products. So a good example would be this reaction right here. Take a moment and balance it for me. Did you balance it? Prove it. Okay. This end? That's what you like? All right, you can read this one of two ways. Here's the key. On the small scale, nope, we're set. On the small scale, you could say that it takes one molecule of nitrogen. This is a 1. I'm going to write it because it's very clear today. 1 molecule of nitrogen plus 3 molecules of hydrogen to make 2 molecules of NH3, which is ammonia. Okay? Every time it takes 1 molecule of this, 3 molecules of that to make 2 molecules of this. Now I know that 1 plus 3 is not equal to 2, but what's happening here is that you're taking, let's see, 2 nitrogens and 6 hydrogens and rearranging them to get into this. You get 2 ammonia molecules, 2 NH3. The total amount of stuff remains the same. The more appropriate way to read that for this chapter is to say that you have 1 mole of nitrogen and 3 moles of hydrogen to make 2 moles of ammonia, which is a lot more ammonia, about 34 grams of it. So this is a more appropriate way, and these coefficients are going to play a key role in what we call stoichiometry, because now the coefficients are called mole ratios. Let's put an exclamation point there. Let's get serious. Should I continue talking? I'm going to. I do want to. Mole ratios. That's the key for all the stoichiometry problems you're going to see today. And here's the most simple kind of problem you would see in example 1. How many moles of H2 are required to react with 4 moles of N2? Now, when you do a mole ratio problem or any stoichiometry problem, you only ever care about 2 things. Get it together. So, in this particular question, all I care about are hydrogen and nitrogen, these 2 right here. I'm asking, if I've got 4 moles of this, how many moles of this will I need to make the reaction happen? Actually, it'll happen with any number, but if you want to use up this exact amount, then you must maintain the ratio. But if I have 4 moles of this, how much of this would I need to make the reaction go to completion? That's what this question is asking. It does not involve this at all. So it won't always involve everything, and it'll only ever involve two things. And here I'm talking about these two. Kind of like saying, if you're making the bike, hey, I've got 55 wheels, how many frames will I need to make some bikes? Or I wanted to make a cake. I have 3 pounds of flour, how many eggs will I need? Okay, it's the same kind of question. You don't care about the end result. You're just saying, you're looking at two things together. Okay, so how does it work? Well, it works like any other conversion. You start with what you're given, which is 4 moles of nitrogen. And this mole ratio, these are now a conversion factor. To get from one spot to the next, you use these big numbers in front, and because that's your ratio. The number you start with, or the thing you start with, always goes on bottom. So from here, that's a 1. You write 1 mole of N2. And the thing you want to get to always goes on top. That'd be 3 moles of hydrogen. And these numbers come from the balance reaction. You probably, well, you may have, if you were thinking about it, done this already in your head, because it's not complicated math. 4 times 3 is 12, and you're just saying that it would take 12 moles of H2 to use up all 4 moles of N2. Make sense so far? That's best case scenario. It gets much worse, because in labs, we don't measure out moles. What do we measure? Grams, most commonly. And so, but this is definitely in moles. It's not grams. I can't say if I had 12 grams of this, what would I say? Oh, sorry. If I had 4 grams of this, I can't say that it would take me 12 grams of this to make 2 grams of, or whatever the amount of ammonia I would make. That's not how it works. It's not a gram ratio. It's a mole ratio. So when you're giving grams, what happens often is that you have to convert your grams to moles first, then use this mole ratio, then convert back to whatever you want your answer to be in. So it's more complicated than just simply this one-step problem. So let me give you an example of that and then tell you the 3 steps again, and then we'll do a couple more examples. So here's my second question. How many grams of ammonia, this time, are produced from 50 grams of nitrogen? There are 3 steps to solve this problem. I'm going to come back to that in a second. If you haven't quite read it, no worries. Any Stoic problem is really solved by 3 steps, especially these mass ones, where you start with mass of one thing and end with mass of another thing. The first step, here I'll write it out, steps to solve stoichiometry problems. Step 1 is convert to moles. I like how I'm in the middle, it makes it brighter. Like it's magic.
What is that?
Magic? Well, science is mostly magic. Probably because there's like a sensor on here, and my hand reflects less light, so it thinks it should be. It opens up its aperture. I'm too much of a camera nerd to tell you. What's that? Is magic? It's varies? Oh, fairies. Yeah, no, it's totally magic. Yeah, it's good. Sarah's not impressed. All right, convert to moles, first step. Then use the mole ratio, which I already showed you how to do. And then usually today you're going to convert back to grams, but you can technically convert to anything that you need to convert to. So I'm going to write convert to whatever your answer is supposed to be in. Yeah, so what you'll use, at least for part of this, is Foldy. So let's go back to our problem we were working on. What do I do with that problem? Oh, here it is. How many grams of ammonia are produced from 50 grams of nitrogen? Your old friend Foldy is back. The first step, if you remember correctly, was to convert to moles. And so always write down what you're given, which is 50 grams, in this case, of nitrogen. Now, I would recommend that you are very explicit with what you are writing here, because you're going to get confused if you don't keep track of your units and stuff, which I know that means nothing to you, but eventually you're going to start getting these wrong because you're not keeping track. But again, you're teenagers. You want to do things the easiest way possible with the least amount of work. I get that. Somehow I respect it. All right, you're right here at mass, and you want to get to moles. That's the first step. So you're at 1 mole over the molar mass. The molar mass of what? Well, we're at nitrogen, so we're going to go with that. So you're at 1 mole of nitrogen over the molar mass of nitrogen. That's nitrogen's 14. There are 2 of them, so you take 14 times 2 is a grand total of 28. Notice how I wrote grams of nitrogen, so I'm very sure that it cancels out there. The second step in our 3-step plan is to use the mole ratio. That's what we did up here. This is the mole ratio. People don't like this. By people, I mean lazy students don't like this, because it sometimes means you have to read this question again. And I know that that's very difficult to read things twice. People kind of get upset by that. So you have to know where you're starting and where you're finishing, and sometimes you need to just look at it again. So it says how many grams of ammonia, that's where I'm finishing, are produced from 50 grams of N2. So I'm starting up here at N2, and I want to get to ammonia. So I'm only involving these 2 things. That's it. I'm not involving hydrogen at all here. The one you start at goes on bottom because you want to cancel it out. That's a 1, so you're at 1 mole of N2 on bottom. The second step comes from the balance reaction, just like it did here. And I want to end up at ammonia, and what coefficient does that have? 2, so you're at 2 moles of ammonia. Now you're done? No. You want to get back now to grams, but now it's grams of something new because this conversion factor allowed us to go from one thing to the next thing. So now we want to get grams of ammonia, so we're right here at moles. We're going to get back to grams. Now we do molar mass over 1 mole, except the molar mass is now of ammonia. So you add up ammonia. Do you remember what it is? Nitrogen's 14, hydrogen's 1. There are 3 of them, so that equals a grand total of 17 grams in 1 mole. When you want to solve a problem like this, just slap it into the old calculator.
I have a question.
Oh, sure, go ahead.
That ammonia was NH4.
That's ammonium. Good question, though. Is that right? No. Yes?
28.
Oh, yeah, 28. Where'd the 17 come from? 50 times 2 times 17 divided by 28. That's better. 60.7 is what I would go with. 60.7. Now make sure you're very good with your units now. It's not really enough to say grams anymore. You probably should say grams of ammonia, so everyone is very clear that you're telling everyone, yes, I know what I'm doing. Grams of ammonia. Notice, I was lazy here. Notice, moles of ammonia cancels moles of ammonia, moles of nitrogen cancels moles of nitrogen, grams of nitrogen cancels grams of nitrogen, and the only thing left is grams of ammonia. And if you read the question again, which obviously you never would because you're teenagers, it says how many grams of ammonia are produced. And so that's what we know that we set it up right. But once again, you're kids, right? And you want to have some sort of quick, easy way to solve these problems, some sort of template to plug them into. Let me try to give you my version of that template right here in case that helps you, which I think it might. You start with whatever number you're given. In grams. On bottom, for all these problems, there could be different problems, and there will be, but for today, this is probably a good start. On bottom goes the molar mass in grams of that thing, of the given, I should say. On top is 1 mole of the given, whatever you're given in the problem. The middle step always comes from the balanced reaction. Heaven forbid that you would stray from the template and think about this on your own, but the middle number comes from the balanced reaction. So it's the coefficient of what you are given on bottom. And on top, it's the coefficient of what you want, which we'll just call the needed. Because everyone wants to feel needed. Not really. From the balanced reaction, Rxn is the reaction. Rxn's reaction. Rxn reaction. Playhouse, baby. Thanks. Just trying to save that. Just trying to save our conversation. This new thing? I got it third hour. Yeah. And finally, you want your answer back in grams. So it's 1 mole of whatever you're needed. There's nothing to fill in there. This is just what you write. And then on top goes the molar mass of whatever you need. MM of needed in grams or grisams. Once again, I wouldn't treat this as the end-all, be-all, because it will differ. And really, it's more important that you know the process of how it works, the 3 steps right here. But for today, if that helps you, then it's great. And if it doesn't help you, then whatever. Want to try another? The answer to that question is yes. You didn't like this thing on Stoic Probs with the hashtag? Too cool for it?
So are we always going to get
Yeah, you always will need a reaction. And I think Marika is thinking forward to a very scary future where one day I won't give you the balanced reaction. Instead, I'll have it in words. Then you'll write it. Then you'll balance it. Then you'll do a whole bunch of math. But right now, for today, you're going to get balanced reactions. And then I'll slowly start with like making you balance them, then doing the problem. Then I'll start with you write it and balance it. Then you do the problem. I know, that's so much fun. Because then I get to give you like 3 problems per class period and just like walk away because it'll take you all hour. Just kidding. I mean, the goal is to make sure that we know how to do the math. I mean, some people still don't know how to balance, and so probably stick to this way for a while. Okay, so can you balance this? Let's start there. You do that while I write the question, which I forget what it was, but I'll track it down. Oh yeah, here it is. So the question, in case you can't see it, says how many grams of oxygen are required to react with 100 grams of pentane, which is the C5H12. You would definitely need a balanced reaction to do this, and so I wrote the skeleton reaction here. But if you balance it, you should balance it in alphabetical order because it's a combustion reaction. So you'd put a 5 here. Oh wait, hold on, sorry. 5 there for carbons, and a 6 here for hydrogens, and 8 there for oxygen. Look at that multicolor presentation today. Which other teachers that you have are doing multicolor presentations today? What do you mean? This is blue. Check it out. Check it out.
use markers?
Here.
Do it.
I can't tell. I just see it bold.
I can't. It's already blue. It's gonna be bad. It's gonna be bad.
Really?
All right, here we go. Do you want to try it first? You should try it first. Do that. Try it first.
You should try.
What? That's a good point. It's hard to argue that.